So good morning, everyone. Welcome to another edition of the FEM at LLNL seminar series. It's my honor today to introduce Professor Vikram Kavini, who is from the University of Michigan. He got his PhD from Caltech in 2007, and he uses finite elements for computing electronic structure, performing electronic structure calculations, density functional theory. It's not the traditional way in which we do things here in the lab, traditional application. But I think it will be very interesting for us. And one thing I wanted to mention is Vikram and his team were finalists for the Gordon Bell Prize in, I don't know, 2-3 years ago. When was it, Vikram?
2019.
2019. All right. And so today he's going to talk about ab-initio calculations for material simulations, and there's finite elements in that. So Vikram, thank you for agreeing to come, and please, the floor is yours.
Thanks, Anyo. Good morning, everyone on the West Coast. It's my pleasure to tell you a little bit about what we've been doing over the past few years. So this is work that has been ongoing. The algorithmic development started much longer ago, but I'll be talking about the algorithmic development as well as development of the computational framework, which has now put us in a position to be able to conduct fast, accurate, and large-scale ab-initio calculations for material simulations. This is joint work with Sambit Das and Vikash Kanango, who are research scientists here at University of Michigan, and a former group member, Fani Mottamari, who is now a faculty member at the Indian Institute of Science. So just to give you a brief background, the starting point of all ab-initio calculations is quantum mechanics. And here I'm writing down the time-independent Schrodinger equation, h psi is equal to E psi, which is essentially an eigenvalue problem. H is the Hamiltonian over here, and it has the following contributions. The first term over here is the kinetic energy of electrons. The second term here is the kinetic energy of the nuclei. This is the electrostatic interaction between an electron at position Ri and a nucleus at position capital Ra, whose atomic number is Za. And then this is the electron-electron repulsion between an ith and the jth electron. And this is the nuclear-nuclear repulsion. So if we look at the wave function depends on the positions of the n electrons, as well as the spins of the n electrons, as well as the positions of the m nuclei. And what is common in quantum mechanics is to do what is called as the Born-Oppenheimer approximation, which says that the nuclei are much more massive compared to that of the electrons. So we can drop this particular operator in comparison to the other operators, and then treat the dependence of the wave function on the positions of the m nuclei to be parametric. So then for given positions of the nuclei, the wave function depends on the positions of the n electrons as well as their spins. But if you look at the computational complexity of solving the many-body Schrodinger equation, the wave function lives in a 3n dimensional space where n is the number of electrons. And this is computationally very prohibitive. Just to give you an example, even if you were thinking about a nitrogen molecule which has 14 electrons, and if we discretize the whole of the real line with just 10 points, we are talking about solving an eigenvalue problem where the dimension is 10 to the power 42. So that's practically not possible. So this is where quantum chemists have come about with many approximations to this many-body wave function. Basically, from an applied math standpoint, many of these approximations can be thought about as low-rank approximations of this high-dimensional wave function. And this is what leads to theories such as the Hartree-Fock approximation, multi-configuration equations, and so on. But in 1964-65, there was this dramatically different approach that was taken by Hohenberg, Cohn, and Sham. And the main statement that they proposed was that as long as you're interested in the ground state properties, the ground state energy is solely a function of the electron density. And electron density is a field that lives in a three-dimensional space. It is a probability density of finding any electron at a spatial location R. And because the theory says that the central quantity of interest is electron density, that is where the name density functional theory comes from. And it's not very difficult to see the veracity of that statement. The energy of any system, which is described by the many-body wave function psi, is given by psi hat psi, and that will always be greater than or equal to the ground state energy E naught. So we can also flip this statement around and say that we can compute the ground state energy E naught by minimizing over all the many-body wave function psi of psi h psi. So here I'm expanding the various components of the H. T is the kinetic energy of electrons. This is the electron-electron interaction. And this is the interaction between the electron and the nuclei, which is essentially can be thought of as the external potential that the nuclei are providing for the electrons to move in. EZZ is the nuclear-nuclear repulsion, which is treated in a classical manner under the Born-Oppenheimer approximation. So now this V external of Ri, this is a single electron operator. That is, it depends at a time only on the position of a single electron. So this psi times this particular quantity in a product psi results in, reduces to this form, which is integral of the electron density times the external potential. But if you look at the first two terms still depend explicitly on the wave function. But we can take this minimization over all admissible wave functions and then split it into two minimizations. One is a minimization over all electron density rho, another a minimization over all wave functions that give a particular electron density rho. Because psi is in a high dimensional space and rho is in a three-dimensional space, this is essentially, you can think of it as a dimensionality reduction. So now if we look at like this particular minimization problem, which is in this round brackets, that gives us a functional f of rho. And if you look at it, there is no information about the system of interest over here. So all information about the system, which is whether it's a piece of aluminum, magnesium, or a molecule, is all in this external potential. So this f of rho is actually a universal functional, which is solely a property of electrons. We know that there exists a universal functional, but we just don't know what its form is, and that's the holy grail of density functional theory for the past, I would say, 50 to 60 years. But what Kohn and Sham did was something clever. So they took this f of rho and then decomposed it into the following form. The first term over here is the kinetic energy of non-interacting electrons. This is the classical electrostatic interaction energy given an electron density distribution rho. So this is just like solving the Poisson problem and computing the electrostatic interaction energy. And all the remaining quantum mechanical interactions are lumped into this term called the exchange correlation functional. So this EXE of rho turns out to be a smaller quantity compared to TS of rho and EH of rho. And all the modeling approximations are now present in this EXE of rho. So while we know that there exists a universal EXE of rho, we don't know again what the form is. And this is where any approximations or any modeling into density functional theory comes about. And there have been many successful models that have been developed over the past 20 to 30 years, which give good transferability across many material systems as well as material properties. But still, this is an active area of research because the accuracy that we get is still not quantum accuracy, and there is a great need to continuously improve the exchange correlation description of density functional theory. But I still have not told you like how to compute this TS of rho. We can compute the TS of rho indirectly by looking at the variational problem over here. So if we look at the Euler-Lagrange equations corresponding to this variational problem, that reduces to what is called as the Kohn-Sham eigenvalue problem. So we have the Kohn-Sham Hamiltonian over here, which comprises of a Laplace operator and an effective field. So this is the effective field or the mean field that every electron sees. And psi I over here are single electron Kohn-Sham orbitals, and epsilon I are the associated eigenvalues. Now, this effective potential has three components. One is the external potential that's provided by the nuclei, the Hartree potential, which is nothing but the Coulomb electrostatic potential corresponding to an electron density distribution rho, and all the quantum mechanical interactions which are in this exchange correlation potential, which is nothing but the functional derivative of this exchange correlation energy. Now, this effective potential depends on the electron density, but the electron density itself is computed in terms of these wave functions psi I. So this can either be viewed as a nonlinear eigenvalue problem, or it can be viewed as an eigenvalue problem where you have to do a self-consistent field iteration or a fixed point iteration to converge your electron density. And once you converge on the self-consistent iteration, then the kinetic energy of non-interacting electrons can be computed in terms of these single electron cone-sham wave functions. And then we can compute the ground state energy. And once we have the ground state energy, then you can compute a host of other properties. That is, you can compute the forces, you can relax the forces to compute your ground state structure, as well as, like, given the electronic structure, you can compute a whole range of properties, understand the IV characteristics, understand the band gaps, and so on. If we look at from a computational standpoint, what is the most expensive part of the density functional theory calculation of solving the cone-sham equations? That is the solution of this eigenvalue problem. And that scales as cubically with the number of electrons in the system, because we have to solve for as many eigenstates as there are number of electrons in the system. There have been approaches like where people have exploited near-sighted principles and then also develop like linear scaling approaches, but they're typically restricted to a class of material systems, such as insulating material systems. But if you're looking for a generic method that applies without any material system restriction, the computational complexity still scales like cubically with system size. But this is still better than the exponential complexity of solving the full Schrodinger equation. So as DFT provides a good balance between accuracy and computational efficiency, DFT is used in a wide range of fields, be it material science, chemistry, chemical sciences, spectroscopy, device physics, you name it. And in fact, like, there was this not so recent article, I mean, it was in 2014, where they surveyed all the highest cited papers across all fields. I mean, this includes psychology, physical sciences, mathematics, everything. And they saw that like 12 out of the top 100 most cited papers were related to DFT, and in fact, 2 in the top 10 as well. So given this vast importance of DFT to a wide range of disciplines, there have been many DFT codes that have been developed over the past 30 to 40 years. And in fact, like, there are almost 100 DFT codes that have been developed. And also you can see that there is this rapid increase in the use of DFT calculations, an exponential increase. In fact, like, if you look at like some of the codes that I listed over here, many of them are based on plane wave basis because it is a systematically convergent basis, and it is highly suitable for solid state calculations. But still, if we look at like the relationship of these DFT calculations to high performance computing, I think this cartoon nicely sums it up. So DFT calculations still operate in this high throughput regime rather than utilizing the available high performance computing calculations for more complex and larger scale calculations. And the main reason is twofold. One is that the existing codes do not scale very well on parallel computing architectures because many of these codes are either based on plane wave discretization, so Fourier transforms may not scale beyond a particular point, or they're based on atomic orbital basis, which again is a global basis, and then one may not like get good parallel scalability. So that limited parallel scalability in conjunction with this cubic scaling complexity essentially puts a lid on the accessible system sizes, and that limits our ability to go to more complex material systems and then be able to do DFT calculations on such systems. But is there a need for like large-scale DFT calculations? And there are many examples where access to large-scale systems like becomes important. So let's say that someone is interested in understanding the catalytic properties of nanoparticles. Even the smallest of the nanoparticles are few nanometers, and then they go to about like 1,000 atoms or beyond. Or somebody may be interested in computing the transport through biological molecules. And these biological molecules typically can be fairly large, going to many thousands of atoms. Or somebody may be interested in understanding the energetics of defects and how it influences mechanical as well as electronic properties. And these defects, if we look at them, be it either point defects, line defects, or two-dimensional defects, these are present in very small concentrations and still bring about a reasonable change in the macroscopic properties. And to understand the electronic structure of these defects, again, we will need access to many thousands of atoms. So what we have been trying to do in our group is to explore if finite element basis is going to help us in addressing this limitation of the existing available techniques as well as codes in terms of accessible system sizes. So this group, like I presume many of you are actively working on finite elements. So clearly one key advantage is systematic convergence. You can either reduce the mesh size or bump up the polynomial order. It provides spatial adaptivity, unlike the plane wave basis, which give you a uniform resolution. It allows for consideration of complex geometries and boundary conditions. But I think one of the key aspects of finite elements is that it has the potential for excellent parallel scalability. It's not that these advantages were not known to people. They've been known to people for a very long time. And in fact, there were many works which explored the use of finite elements for electronic structure calculations, in fact, dating back to the mid-1980s. But what people saw in these studies was that there was a huge degree of freedom disadvantage. And when I mean degree of freedom disadvantage, if I may elaborate, if we want to get to chemical accuracy, which is the accuracy to which you want these calculations to be converged to, these are relative accuracies of the order of 10 to the power minus 5 or better. So to get to this kind of relative errors, one needed almost a million basis functions per atom to get to this level of accuracy. And that compared very poorly with the other basis sets, be it plane waves or atomic orbital type basis functions. But many of these studies which were initially exploring the use of finite elements, they were looking at primarily linear and quadratic finite elements, because that is mostly what we use in engineering type applications. But as I mentioned to you, the chemical accuracy is much, much more stringent than the accuracies that we seek to go to in engineering applications. So what we looked at almost 10 years ago was if higher order basis sets or higher order finite element basis functions would essentially give us any advantage. And to emphasize the importance of using higher order finite element basis for DFT calculations, let me just demonstrate that with these two examples. One is a copper nanoparticle with 55 atoms, and this is a periodic simulation, which is a molybdenum periodic supercell with a vacancy over here, again has around 50 atoms. So here I'm showing the number of finite element degrees of freedom that one would need as a function of the polynomial order to get to chemical accuracy. So as you can see, even for roughly a 50 atom simulation, one would need almost 5 billion degrees of freedom to get to chemical accuracy for this copper nanoparticle. But if you go to a fourth order finite element and beyond, like that reduces by almost 1,000-fold. But as we are going to higher order polynomials, then the bandwidth of the matrix increases. There's also a corresponding increase in the quadrature rule requirement. So would that translate to a computational efficiency? And then it does. We also end up like seeing that we get almost 1,000-fold advantage even in terms of computational efficiency as well. So the second challenge, or rather, the other advantage of finite element basis is spatial adaptivity. So in these works, like we have constructed error estimates for the ground state, error in the ground state energy in terms of the finite element mesh size. And we don't have to treat the finite element mesh size to be uniform, but like this can be adaptive. So by minimizing this error metric with respect to the finite element mesh size distribution, subject to a constraint that the total number of elements be fixed, we can actually get also adaptive, a priori adaptive mesh refinement. And that again cuts down the degrees of freedom by another 5 to 10-fold for many systems. The second challenge of the finite element basis is that it's a non-orthogonal basis. So when we discretize this problem, we end up with a generalized eigenvalue problem. And the available techniques for a generalized eigenvalue problem are fewer compared to standard eigenvalue problems. So one can take a generalized eigenvalue problem and convert it into a standard eigenvalue problem using the Loudon orthonormalization. But this still requires you to compute the mass matrix, take its square root, and then take its inverse. And especially when we're talking about like very large scale problems, the evaluation of this m to the power minus half can become the rate limiting step and a key bottleneck. So what we have done is, instead of using the conventional finite elements, like where the finite element nodes are equispaced in a finite element, we use spectral finite elements, where the nodes of the finite element are at the roots of the derivative of the Legendre polynomial. So one advantage of using the spectral finite elements is that as you keep going higher order in P, it gives you better conditioning compared to the conventional finite elements. As well as the other key advantage is that if we use a reduced order quadrature rule, which is the Gauss-Lobato-Legendre quadrature rule, the quadrature points are actually coincident with the finite element nodes, and that makes the mass matrix to be diagonal, and thus transforming the generalized eigenvalue problem to a standard eigenvalue problem is then trivial. I should note that we only use this reduced order quadrature rule in the evaluation of the mass matrix, but we use the full quadrature rule when it comes to, or full Gauss quadrature rule when it comes to evaluating the Hamiltonian matrix elements. Okay, so now that we have a discrete standard eigenvalue problem, solving this problem is also computationally challenging because we are talking about solving as many eigenstates as there are number of electrons in the system. And some of the larger problems that we did, like N was closer to about like 100,000. And so try to compute those many number of eigenstates can be challenging. So, but there is a key aspect of the nature of the cone-sham eigenvalue problem that we are solving, which actually comes to our rescue. So the eigenstates that we are trying to solve are at the lower end of the eigenspectrum because we are interested in the ground states. All the eigenstates that we're interested in are at the left end of the eigenspectrum. So if this was the eigenspectrum and I call the spectrum of states like that I'm interested in to be the wanted spectrum, and then these are the states that I really don't care about, then if we scale and shift the Hamiltonian such that the unwanted spectrum maps between -1 to 1, then we can use a Chebyshev filtering technique to get a subspace which is very rich in the wanted eigenspectrum. So the main idea is that if we take a Chebyshev polynomial of the scaled and shifted Hamiltonian, the Chebyshev polynomials have a property that they are pretty much close to order 1 between -1 to 1, and then they rapidly grow outside of -1. And when we hit the Chebyshev polynomial filter on a bunch of vectors, size over here, what it does is it kills the components along the unwanted spectrum and then magnifies the components along the wanted spectrum. So this eventual space that I end up with, which is denoted as this filtered vectors, is going to be very rich in the wanted spectrum. And hence, I can then project this particular problem into the wanted spectrum or this Chebyshev filtered space that is a close approximation to the wanted spectrum, and then solve a smaller eigenvalue problem. So that's the general strategy. The other advantage of this filtering technique is also that Chebyshev polynomials or the action of the Chebyshev polynomial filter on a bunch of vectors can be written as a recursive relation. So all I need to be able to do efficiently is an operation which is h times x to compute this filtered vectors. So as I mentioned to you, so this is the broad numerical algorithm. So we start with a guess for the initial electron density. We compute our discrete Hamiltonian in the finite element basis. And then we construct the Chebyshev polynomial filter and get the filtered vectors. Now, the filtered vectors that we get are not necessarily going to be orthogonal. In fact, they won't be orthogonal. So it would be beneficial to orthonormalize them because then the projection into this particular filtered space becomes easier. So we have an orthonormalization of the Chebyshev filtered basis, and then we project the original eigenvalue problem into this Chebyshev filtered subspace. And that then gives us a smaller Hamiltonian, which is roughly the size of number of electrons by number of electrons. And then we can diagonalize that Hamiltonian either depending on its size, either by direct means or iterative means. And then we can rotate back the solutions of this eigenvalue problem into the original finite element subspace and then compute the electron density from those Kohn-Sham eigenfunctions that we computed. If the output electron density is the same as the input electron density, we're done. Otherwise, we have to do this fixed point iteration, which is achieved through some mixing schemes of the electron density. So that's the overall algorithm. But if we look at the computationally most intensive steps in this whole numerical algorithm, that would be these three steps. So the Chebyshev filtering scales as order mn, where m is the number of finite element basis functions and n is the number of electrons. And these two steps scale as order mn square. But then the prefactor for these things is a bit smaller compared to the prefactor for the Chebyshev filtering step. So even for systems of the order of like 30,000 to 40,000 electrons, this will be the dominant step. So now I'll briefly go about like the HPC aspects of how we accelerated each of these three steps. So as I mentioned to you in the Chebyshev filtering, the main kernel is h times x, where h is a sparse m by m matrix, where again, m is the number of finite element nodes. X is going to be a dense matrix. So this is what like is the solution, the trial vectors corresponding to the Kohn-Sham wave functions. It's of the size order m cross n, where n is the number of electrons in the system. And the output y will also be a dense matrix of m cross n. So for some of the larger problems that we did, m is roughly of the order of like 300 million, and n is roughly of the order of around 60,000. So this X matrix has about 18 trillion entries. So that's the kind of size of the problems that we are talking about when we're trying to go to like larger scale DFT calculations. So if we were to do this h times x operation in a naive manner, in a matrix-free way, we might not be as efficient. So what we did is, of course, there is a domain decomposition step, like where each color represents like one of the partitions. And in each of the partition, what we do is instead of doing this at the global level, we try to do the h times x operation at the elemental cell level and then assemble back this y vector. So to do that in an efficient manner, the storing of the entries like matters. So for each of the finite element degrees of freedom, we store all the values of the n wave functions in a contiguous manner. So that allows us to extract the relevant like degrees of freedom corresponding to a block of wave functions in a very easy manner. So when we do this h times x, we don't like take the full x corresponding to all the n wave functions, but we only do it for a block of wave functions, because if we don't do that, then the we can substantially increase the memory footprint, which is counterproductive. So for this block of wave functions, then we can go and then extract out the elemental values for each of the elements. And then once we extract out the elemental values, then we can go and then do the h times x using strided batch x gems in a very efficient manner. Then we get the cell level entries for the y matrix. But then we have to assemble back, and there are two assembly operations that we need to do. One is the assembly of the nodes which are sharing multiple elements. So for that, like we use atomic operations if we are doing this on GPUs. So that's the local assembly that's happening. And then there is another assembly operation that happens across the partition boundaries. But the number of typically, the number of nodes that are on the partition boundaries are far fewer compared to the number of nodes in each of the partitions. So here is where we also use a mixed precision strategy, where the communication that is required to do this interpartition assembly is done in single precision, FP32, as opposed to all the calculations which are done in FP64. And because we are doing this h times x for each of the blocks of wave functions, we can also overlap the compute and communication of the blocks. So while the communication of one of the blocks is happening, the compute of the next block can actually begin. So this is the performance of the Chebyshev filtering on Summit, and this is for a system with about 1,000 electrons. So as you can see, as we increase the block size, we get like very good throughput performance and go above 25% on Summit. In fact, this is for finite elements like of the order. I think this one was for a fifth order polynomial. But if we go to like seventh or eighth order polynomial, the throughput performance actually goes up to almost 45 to 50%. And in terms of the reduction in the wall time, we see a substantial reduction of almost 20-fold and giving us good CPU-GPU speedups. So the second step is the orthogonalization step. And the way we do this is we compute the overlap matrix and then do the Cholesky decomposition and then construct our orthogonal wave functions which span the same space. So the space is unchanged over here. But even again, when we're doing this overlap matrix communication, we can bring about the mixed precision strategies. One is, so as the self-consistent field iteration is going on, what happens is that the wave functions will become very close to the eigenfunctions. And if that is the case, then this overlap matrix becomes diagonally dominant. So which is the reason like we do double precision arithmetic for evaluating the diagonal entries of this overlap matrix, and then use single precision for the off-diagonal entries. And similarly, when we are assembling the orthogonal vectors as well, we can use the same trick. And again, in this step too, we use the blocked approach to reduce the peak memory, because if we have to evaluate this particular S matrix in each partition, and we want to do that for all the number of electrons in one go, the peak memory can go very high, because this is going to be a dense matrix and n can be as large as 100,000. So again, we do this blocked approach where we go block by block. And because we're using this blocked approach, we can overlap compute and communications again. So this is the basic strategy, as I mentioned, of overlapping compute and communication, where while the compute of the other block is happening, the communication and then the copy operations of the previous block can be happening simultaneously. So this is essentially the performance that we got with a 60,000 electron system on 1,300 Summit nodes. So if we were doing the evaluation of the Cholesky Gram-Schmidt procedure in double precision, that's the throughput performance that we get. If we go to mixed precision, that increases by almost 50% to twofold, and then we get another 50% boost, like, if we overlap the mixed precision, if we overlap the mixed precision with the communication and compute. So the final step is the Rayleigh-Ritz procedure, where we project the problem into this orthogonal Chebyshev filtered subspace, and then we diagonalize in the smaller H hat, and then we compute the wave functions in the finite elements space by the subspace rotation procedure. So even over here, like there is a strategy like where we can do some so-called spectrum splitting to take advantage of mixed precision compute as well as overlapping compute communication. The main idea is that the basic quantity of interest is the electron density, and the orbital occupancy for all the deep states is going to be 1. So that's the Fermi-Dirac distribution. It's 1 and then changes from being 1 to 0 right around the chemical potential. So we actually do not need explicitly the eigenstates for the states where like the occupancy is 1. As long as we have the subspace that is good enough, like we can compute the electron density. And that is the reason wherever we are talking about, so we can split the states that we want into an occupied space and a fractionally occupied states. And for the fully occupied states, we can do the computation in single precision. It's only in the fractionally occupied states we would need to do double precision. And so we can bring about a mixed precision aspect, like even in this particular step. And again, you can see that there is a substantial benefit from going from double precision compute to mixed precision algorithm, and a further boost, like when we overlap compute and communication. So as I mentioned to you, like we've been using mixed precision in multiple steps. So how does this affect the accuracy as well as the robustness of the calculation itself? So here I'm showing for a wide range of material systems what the error that we are getting in the energy per atom is for a mixed precision calculation with respect to a single precision. For a mixed precision calculation with respect to a double precision calculation. And you can see that the error is fairly small for the ground state energy, as well as the error in the forces is also much lower compared to the desired tolerances to which like we would want to converge the forces. And in terms of robustness, the number of self-consistent field iterations are not changing. So that shows that the mixed precision aspects are not polluting the calculation. So putting all these things together, like we developed the DFT-FE code, which is an open source code. And here I'm providing some comparisons with Quantum Espresso, which is one of the widely used plane wave codes out there. And here as a benchmark system, I'm considering single vacancy in BCC molybdenum. And we're solving both the codes to the same level of accuracy, which is the chemical accuracy. And we consider various system sizes, cell sizes going from about 400 atoms all the way to 2000 atoms. So these are the number of node hours one would need for a single SCF iteration on Cori KNL. And as you can see, once we start going to larger system sizes, we see almost 10 to like 20-fold advantage over Quantum Espresso. And one thing I want to emphasize is that this is a periodic calculation where the plane wave basis is the most efficient. So here I'm showing a non-periodic calculation, which is a copper nanoparticle, again with particles with increasing number of atoms. And the crossover happens much earlier for these non-periodic systems. And even at around 500 atoms, like we are almost 10-fold faster compared to Quantum Espresso. Or 10-fold more computationally efficient, I should say. And so this is the strong scaling of DFT-FE and presented for a system with about 2000 atoms, around 20,000 electrons. And this is on the Theta machine, and this is on the Summit GPUs. And you can see that we scale fairly well to many tens of thousands of MPI tasks, as well as many thousands of GPUs as well. And I think, like, for practitioners of DFT, I think this slide will be the money slide, like where here I'm comparing what is the minimum wall time per SCF iteration that we can get for the DFT-FE code and the quantum espresso code, such that the parallel scaling efficiency doesn't fall off below 40%. And here I'm providing the comparison on NERSC Cori for the CPU comparison. And then I'm also providing what the minimum wall time we get for GPUs is. And as you can see, once we start going beyond like 5,000 electrons or so, we see almost a 10-fold reduction in the minimum wall time requirement for DFT-FE compared to quantum espresso. And then we see another 10-fold drop when we use GPUs with DFT-FE. Quantum espresso also has a GPU based code, but then it cannot scale to multiple nodes. So it works well, like, on few nodes, maybe 1 or 2 nodes, but then the scaling falls off pretty dramatically. So as you can see, DFT-FE is able to take advantage of the leadership class computing facilities and architectures and be able to like do large scale calculations in a fast manner and at the same accuracy as that is provided by state-of-the-art code, plane wave codes. So here is an overview of what are the capabilities of the DFT-FE code. So this article over here describes like our initial paper, which pretty much like laid the foundation. And then this article describes the GPU extensions of the code. So the discretization is based on adaptive finite element basis. It can handle periodic, non-periodic, semi-periodic boundary conditions. It can do both pseudopotential and all electron calculations in the same code. At the present moment, like we have density-based exchange correlation functionals, but we also have in-house implementations of hybrid functionals. The code can compute ground state energies. It can do geometry relaxations, both ionic and cell relaxations. You can do Ab-initio MD calculations with this. And the scaling has been tested on Summit, Theta, Stampede, Comet. We went up to like around 200,000 MPI tasks on Cori, and we went up to 24,000 GPUs on Summit. And we've demonstrated calculations on about 100,000 electrons, pseudopotential calculations, as well as 10,000 electrons, all electron calculations. And we do see very good sustained performance on Summit, around 64 petaflops at about 38% efficiency on Summit. We also have extended the GPU code to take into account HIP. So we are testing this thing on Crusher and Frontier at the present moment, and we are seeing good efficiencies even on Crusher, close to the 35 to 40%, like at the present moment. So what are the kinds of problems that we can tackle with such a code? So one of the applications that we are particularly interested in is understanding the reasons behind the low ductility in magnesium and trying to see if we can do something from a metallurgical standpoint to improve the ductility of magnesium, because it has a technological importance also of improving fuel efficiency and carbon footprint by reducing the weights of the vehicle. So the main limitation of the limitation of reduced ductility in magnesium compared to other structural materials that we have, it has partly to do with the behavior of dislocations in magnesium. So magnesium is a HCB material, whereas if you take something like an aluminum, it's an FCC material. And when you have FCC materials, like you have many slip planes on which dislocations can form as well as glide. The number of planes that are available for dislocation activity is much higher. Whereas if we look at magnesium, the dislocation activities is predominantly on the basal plane. The prismatic planes are pretty much not accessible to any dislocation activity because the energies of dislocations on these prismatic planes is quite high. There has been evidence, experimental evidence, that dislocations can form on these so-called pyramidal planes. And one of the things that people have been trying to achieve was, can we alloy the magnesium metal in such a manner such that we can enhance the dislocation activity on pyramidal 1 and pyramidal 2 planes. But what people saw when they did atomistic calculations is that any dislocation on pyramidal 1 or 2 plane actually dissociates into partials on the basal plane and gets locked up. So this is not a glissile dislocation, that is not a dislocation which can glide. So people have hypothesized that by adding certain solute atoms, you can avoid the dislocation from, or reduce the rate at which the dislocation falls from a pyramidal plane to a basal plane, but maybe you can get a cross slip, that is dislocation jumping between pyramidal 1 and pyramidal 2 plane, and thus enhance the ductility of magnesium. But one of the things that people were not able to, and for all these models, one of the key aspects that the metallurgists were keen to get an estimate of was, what is the energy difference of a dislocation lying on the pyramidal 1 and the pyramidal 2 planes. And this energy difference is actually a small quantity and highly sensitive to how you do the DFT calculation and the cell size that you're doing the DFT calculation on. So people were not able to even get the sign of this particular energy difference right. But because we had DFT FE, which provided access to very large scale calculations, we were able to do a systematic cell size convergence. We went all the way up to 3,700 atoms or so. So this particular calculation had 36,000 electrons in the periodic unit cell, but also 12 K points. So the number of wave functions that we were computing were 12 times 36,000, so which is quite large, as you can see. And these are fully relaxed calculations. So we are doing full ionic relaxations. It's not just for fixed positions of atoms that we are computing these energetics. So this is a quantity that we were able to compute, as well as another interesting thing that came out of the study was that this energy difference was not a constant, but this was actually dependent on the macroscopic strain that was coming at the dislocation core. And this macroscopic strain could either be because of processing conditions or existence of other dislocations or defects at a given dislocation core. And so we've taken all these particular inputs, and then we have actually are working on a mechanistic model which is able to predict many aspects of experimental results. And this is something that we are currently writing up. And another aspect of improving ductility is being able to enhance non-basal structures, non-basal textures in grain boundaries. That is trying to make sure that the grain boundary does not rotate to becoming predominantly along the basal direction. So if you have a good rich diverse grain boundaries along different which have a non-basal structure, it can actually promote the dislocation activity which be in the other planes as well. And from a polycrystalline standpoint also, this is going to be very helpful. So one of the key aspects of understanding the way grain boundaries migrate is based on the energetics of the grain boundary solute interactions. And then computing this segregation energy at the grain boundaries again requires very large scale system sizes involving many thousands of atoms. And this is something that is now possible as well. And there are a couple of other examples that I've given over here where DFT FE helped in terms of providing key insights. In this particular work, this was actually experimentally motivated, where collaborators in Israel, they took a DNA molecule and then they scissored the backbone and then measured the IV characteristics and saw that the current across like a particular DNA molecule was completely suppressed. The conventional belief of like quantum transport or electron transport in DNA molecules is that it happens primarily via base pairs. So by scissoring a backbone, you should not like see that the current is significantly suppressed. So this is where they started like thinking that actually backbone also may play an important role in terms of controlling the electron transport. So they approached us to be if we could do and do such calculations and be able to like look at the electronic structure of a large DNA molecule involving about 100 base pairs. This had about 6,200 atoms. We were able to do that, and this is the local density of states on the backbone and base pairs. And as you can see, once you start like applying a voltage beyond beyond about 1 eV or so, there are actually states which allow for transport across the backbone as well. And in this work, like which was a collaborative work with Julia Gali, they were interested in understanding or computing spin Hamiltonian parameters because they were interested in understanding the coherency timescales of spin qubits. And computing spin Hamiltonian parameters is a very challenging aspect because existing basis sets, which are primarily Gaussian or augmentations to Gaussian basis sets, they do not describe the electron cusp right near the nucleus. So trying to get quantities such as Fermi contact energies as well as hyperfine tensors is going to be very tricky unless like you have a systematically convergent basis set. And since we have a systematically convergent basis set using DFT-FE, we were able to do these calculations. And so far, like I talked about pseudopotential calculations, but the finite element basis can also be advantageous for all electron calculations as well. But the key aspect about just using a classical finite element basis for all electron calculations is that the number of basis functions that you need is very large, like again 10 to the power 5 to 10 to the power 6, despite using higher order finite elements. So this is where we are exploring an idea of can we enrich the finite element basis with single atom Kohn-Sham orbitals, which can substantially reduce the basis set requirement and be able to like allow us to access much larger scale DFT calculations, all electron DFT calculations. So the idea of enrichment is not new, like people have explored this before. And the key advantages of enrichment, as I mentioned, are one is the substantial reduction in the degrees of freedom that you will get, as well as it will improve also the eigensolver because it reduces the spectral width of the discrete Hamiltonian. Especially when we are using Chebyshev filtering, we can get away with a much smaller Chebyshev polynomial filter than otherwise if we did not have enrichments. And this essentially shows the convergence of the ground state energy for two different finite elements. This is a second order element, and this is this would be a third order element. You can see that the slopes which give you the convergence rates are pretty close to twice the polynomial order. And when we compare the calculations of this enriched finite element basis with other techniques that are available out there for all electron calculations, such as LAPW and LAPW plus localized basis sets, as you can see, there is a very good agreement in the energies that we get, but we're able to access and go to much larger scale calculations than many of these LAPW plus LO codes. So again, a comparison of computational efficiency and scalability, we get a substantial boost in terms of LAPW calculations by using this orthogonalized enriched finite element formulation that we have, as well as because it's a finite element basis, we also scale very well on parallel computing architectures. So I'm almost out of time. So I just want to mention that we're also working on improving the accuracy of the exchange coalition functional itself in density functional theory. The main idea is as follows. We are doing mini body quantum calculations, which are only accessible for very small system sizes. These are accessible for maybe system sizes of the order of tens of electrons to maybe 100 electrons or so. So for each of the system, we're computing the electron density and the ground state energy. And then we're solving the inverse DFT problem, where we are evaluating what is the exchange correlation potential that gives back the same density as that of the full quantum calculation. So if we're able to compute this, that would be the exact exchange correlation potential corresponding to that electron density. And once we have this for various systems, then it becomes a data-driven problem. Can we then go after the exchange correlation functional learning, having this particular data? But one of the key limitations of realizing this framework was the solution of the inverse DFT problem itself. And we were able to like solve this problem. While the problem is straightforward in terms of a formulation perspective, it is numerically a very challenging problem. And we were able to like solve this problem to tight accuracy. And then this article over here like describes the approach and also presents the results of the good accuracy that we're getting for the exchange correlation potentials. And now once we have the exchange correlation potentials, we are now also going and after the learning problem, which is trying to improve the exchange correlation functional description in density functional theory. So I might not have the time to go over those aspects, so I will skip that, and then I'll be happy to talk with any of you who are interested offline about this, and then I'll take to the conclusion slide and then be happy to take any questions.
All right. Thank you very much, Vikram. A very, very interesting talk. Let's give Vikram some virtual applause here.
Thank you.
Okay. Yeah, I've been aware of some of this work, but it was really great to hear all the details. All right, questions for Vikram? Anyone? Lots of interesting things. Okay, while we're waiting for other folks, let me ask a question. You mentioned the batched matrix, dense matrix operations. What do you use for that? Is this something you wrote? Do you use a library? What do you use on CPUs and GPUs?
Yeah, this is pretty much written internally, Sanyu.
Mm-hmm.
So the only thing, so the finite element framework that we are using is based on deal 2. But when it comes to doing this batch gems, so the only thing that we rely on deal 2 is essentially the boundary communicator maps. That's it.
Mm-hmm.
So everything else, like once we have the Hamiltonian matrices, everything else, like these storing of these Hamiltonian matrices, the extraction of this finite element nodal values of these wave functions, and then the batch gems have been written internally. But of course, like here, when it comes to like, strided batch gems, like we use like existing operations like cuBLAS operations, which are provided like, GPUs as well as the corresponding gem operations in BLAS and LeapBack.
Have you tried using something like Magma for this?
We have, so where we tried to use Magma was in the solution of this eigenvalue problem. So once you project the problem into the Chebyshev filtered subspace, then we have to solve an eigenvalue problem over here.
Mm-hmm.
And this can still be a largish eigenvalue problem. So it is, we typically go up to like, not typically, but like the largest systems that we have done go up to about 100,000 electrons. And 20,000 to 30,000 electrons is the regime, like, where we are routinely doing some applications. So one of the limitations I feel of Magma is the multi-node aspect. So if we use, so here when we're solving this eigenvalue problem, we use LPA over here. If we look at like what is the minimum wall time that we can get like by scaling LPA over many cores that are accessible versus using Magma, which is still limited on a single node, there's still a huge difference.
Okay. All right. And you've also looked at using Magma for the batched computations, right? Because that's another thing it's good at.
Okay, that we have not
Recently.
tried. So that's good to know. Like, that's
That
something.
might be useful. We recently
Yeah.
had some success with that.
Okay.
All right. Other questions? I see Stefan posted something in the chat. Stefan, do you want to unmute and ask?
Sure. First of all, thank you for your great talk. I had just noticed that your meshes don't look compatible, so I was wondering if they don't need to be, or if you're enforcing some edge constraints on the cells.
They are compatible from what I mean by compatible here is that the basis functions are C0 continuous. So we're using the deal2 framework. So it is the edge constraints are being enforced over here.
Yeah, that's the same in FEM. We have on non-conforming meshes like that. You have a constraint that imposes the continuity that you need, in this case, C0.
Yeah.
Gotcha. Thank you.
Okay, other questions? So while we're on this slide, I have another one, and I'm sorry, I have forgotten. Is there a constraint in deal2 in how much refinement can you do from cell to cell? Does it have to be 2-to-1, or can it be more?
Yeah, it is 2-to-1.
Okay, and so from that perspective, will there be an advantage if you can refine much more around the integral, around the atoms here?
Yes, I think having the ability to coarse grain. In fact, I would say that having the ability to coarse grain more smoothly or lesser than 2-to-1 may be beneficial.
I see.
Which can reduce the DOFs. And again, depends on which regime you're doing the calculations in. For pseudo-potential calculations, a bit more gradual change would be more beneficial. That can actually reduce the number of DOFs. What we see right now is that because deal2 cannot give us that, we're forced to be pretty much close to uniform in the region where a lot of atoms are there, and then the coarse graining is away from the atoms. But when it is all electron calculations, yes, that would certainly be an advantage, to be able to coarse grain faster than 2:1. So having that flexibility would certainly be useful.
Yeah, that's something that FEM can do.
Yeah. So we're not in any way married to deal2 over here. So as I was mentioning, Sanio, we are trying to wean out as much as we can, not tie ourselves to a given finite element framework. The only key thing that we are actually tying ourselves to here in deal2 is those boundary communicator maps, doing the decomposition and creating those boundary communication maps and those constraints. That's pretty much everything else we are doing in-house. And we are also working on the next version of DFT-FE, which has this enrichments automatically built in, which is the enriched version of the finite element basis. And that is where we are trying to be very deliberate and then make sure that all the operations are fairly decoupled from tying ourselves closely to deal2. So I think that is where we also would want to have the flexibility of swapping out one framework for another, and yeah, so that's something I would be interested in talking to you and then seeing how we can probably use FEM in this regard.
Yeah, same here. Okay, other questions? So you briefly mentioned Crusher. What's your kind of general experience with NVIDIA versus AMD GPUs? Do you see the performance you expect? Did you have to do a lot of changes to get the performance you expect?
Yeah, so I would say like we did not have to do a lot of effort in kind of changing from uh, uh, cuBLAS or CUDA programming to HIP. So we did essentially a house cleaning step, like where um, all the aspects which are going through the GPU, like we have a device agnostic like layer which handles um, below which, like, all the differentiation between um, uh, AMD GPUs or like, HIP and then CUDA is coming about. And what we see is that if we were to like take the vendor advertised um, performances of node performances, or the peak performance of these nodes, we are seeing that we are able to get a close to about 3x speed up uh, from a summit node to a crusher node or a frontier node.
Yep.
It is a bit lesser than, like, the 4x, which is in terms of the theoretical peaks, because because we are not solely compute bound, we are also memory bound. And from a node to node comparison, I think the compute has increased by close to 4x, but the memory bandwidth has increased only by 2x. So we are kind of somewhere in between.
Oh, that's interesting. I thought that with these operations, you guys are mostly compute bound. So you also have a memory bound?
Yeah, because if you, as I was mentioning, if I go to the slide, so when we're doing this operation, this is a dense matrix, and we are storing the number of M can be of the order of like hundreds of millions, and N can be of the order of tens of thousands.
Mm-hmm.
So this is a dense matrix, like, and we're accessing these wave functions when you're doing this h times x. And well, when we go and then, like, pull out these even in a strided, like, access manner, we have to pull out these DOFs, and then so this copy and then access operations can control the costs.
Interesting. Okay, I think Brandon has a question. Brandon, please unmute and just ask.
Sure. Thanks. Yeah, this was a really interesting talk. I didn't know much about electronic structure. I hear about them, but that was very clear. I feel like I got some essence of it. So thanks for that, and also how you guys where to focus, where you sped it up. So that was great. I was wondering if, given the structure of these problems, if are there obstacles, or do you think it would be feasible to get design sensitivities to write, adjoint solves out of these around the eigenvalue and all these other and the other diagonalization and these things? If you think it could be feasible to get to a space where you're like then not just be able to compute electronic structures, but maybe even try to figure out how to get the ones you want, is that are there mathematical barriers to that, or is it just implementation effort?
Yeah, so I may be answering this question in a slightly more tangential way, Brandon, and then so since you bring up the notion of adjoints, like, associated with this either eigenfunctions or eigenvalue problems, that is essentially at the heart of actually solving this inverse DFT problem. So because we are interested now, it's not that we're given an exchange correlation potential when we're computing the eigenfunctions and from that the density, but now we're given the density that's coming from a many body wave function calculation, and we're trying to extract that exchange correlation potential that is giving you the same density. So we solve that as a PD constraint optimization problem, and because we have to enforce this as a constraint, we have adjoint functions, like, which enforce that constraint, and then we end up like getting each one adjoint function for each eigenfunction that we are interested in. And then the solution to that adjoint problem also is a is a multi-vector, like, solution of something like a Poisson problem. It's not really a Poisson problem, but something like a Poisson problem. So I don't know if I answered your question, but is that the adjoint aspect that you had in mind, or something else?
It's definitely part of it, right? It's definitely I get, and it might be that my question is not clear because I don't understand the field like you do, but it is part of it, right? There's a lot of self-adjointness going around this. It's the Schrodinger, the operator is nice in this way, right? But so I guess I'm saying, so taking a step back, then is it feasible in some way to get out of this, not just the forward of like what electronic structures do you get, but to sort of say you had those magnesium, you want to try to figure out what kind of grain boundaries you need to, you said some objective functional where I want certain kinds of energies, say like I want certain kinds of glide systems, I want certain kinds of, you get what I'm saying, right? Can I work out what the grain boundary structure, what the electronic structure would need to be, how would I need to dope this thing to get that? You see what I'm saying? Like to get the inverse problem.
Yeah.
Is there like given that is what you just described, do you think that's a feasible thing, or am I describing something that's possible?
So the inverse problem is precisely like, okay, so if it is in terms of like controlling the energies of the grain boundaries itself, that's hard. So because you're trying to map something from a very high dimensional space to a single like energy quantity, and then there's so much of possibilities like that would give you the same energy that the inverse problem will be like very, very ill-posed, and probably practically it may not be tractable. Um, uh, Now, if it is in terms of electron density maps, you would be able to do that, like, using the inverse problem that I just described. But its practicality is no longer there, because then the question is also, how do you go from the electron density maps to the structure of the grain boundary itself? And then there's another inverse problem over there. So.
I see. Yeah. Well, thanks. That was it. Thank you very much.